Today we want to talk about solving equations involving trigonometric functions. Before we begin, I want to point out that there will not be a Zoom meeting on Wednesday. There will be a regular in-person class meeting on Wednesday. I just won't be able to run Zoom on Wednesday. Offer only applies to Wednesday. Come next Monday, we'll be back to our normal schedule. But for Wednesday, we have a different, it's going to be set up differently. So no Zoom on Wednesday. Just the in-class, just the in-person portion of things. Today we want to solve some trigonometric equations involving trigonometric functions. And we want to start with this one. Something actually sine of theta is equal to 1/2. We should already be thinking of 30 degrees, already be thinking of pi over 6 radians. So hopefully we've been conditioned to think that right away. If not, that's okay. We're going to be solving the problem. Now we're looking at this equation in 3 different contexts. And it's going to change how we think about the problem. In part A, we say theta is an acute angle in a right triangle. Part B, theta is an angle in standard position. And theta is between 0 and 360 degrees. And then in part C, theta is the place or places where the graphs of y equal 1/2 and y equals sine of theta intersect. So we're looking at this in the 3 different contexts we've been dealing with angles, acute angles and right triangles, not just angles in standard position, not just angles as we graph them into sinusoidal graphs. So let's see how the context changes each of these problems. In part A, theta is an acute angle in a right triangle. So let's draw a right triangle. Theta is an acute angle in a right triangle, and sine of theta is equal to 1/2. When we think in terms of acute angles in right triangles, we think in terms of opposite, adjacent, and hypotenuse. And we remember our definitions of trig functions, where sine is opposite over hypotenuse. And we know that when we have a hypotenuse of, we can make a hypotenuse of 2 and an opposite of 1. We can just pull the fraction apart and say the opposite is 1 and the hypotenuse is 2. We can also make the hypotenuse equal to a 1 and the opposite equal to 1/2. So we can think of this 1/2 as a 1 over a 2. But trig functions in right triangles are defined as ratios. And this is the same ratio as an opposite of 1/2 and a hypotenuse of 1. So I can just draw a right triangle that's half the size of this one, and we'll have the same angle. In either case, we know that this angle corresponds to 30 degrees. Sine of 30 is equal to 1/2. We know that just because we know that. We also can find this out if we want to calculate it using an inverse trig function. So we can grab our calculating machines. So we either know this or we can calculate it with inverse trig functions. We either know this because we remember, or maybe we're not confident. We're going to grab our calculating machine and use an inverse trig function. We're looking for an angle. That means we're going to be using an inverse trig function. First of all, in this context, since it's an acute triangle, we're going to make sure that we are in degrees. We'll want to be in degree mode. So here we are in degree mode. And we're going to do looking for an angle. So we'll do the sine inverse of 1/2. And it'll tell us that this is a 30-degree angle. It makes sense to answer this question in degrees because if we're talking about acute angles of a right triangle, we're going to be speaking in degrees. Degrees is the language of measuring triangles. When we're talking about triangles, it makes most sense to just list our angles in degrees. So we'll do that. Theta is equal to 30 degrees. Question. Problem that goes way back to the beginning. I should make this the lead question on final exam. Here. Sine of theta is equal to 1/2. Maybe it's too early to use the word final exam. We only use 12. But it's also Halloween tomorrow. I carved a pumpkin, and on the pumpkin it says final exam. It's like college students today. I have another pumpkin that says third paper due tomorrow. You have to go get started on your term paper? No, I have to email my professor and ask for an extension. No, that was my credit. When we run out of candy, I have a special set of pumpkins. They're all filled. And a fraction. 1/2. Simplify the fraction. It's like 2/3. You're like, well, I can't say it's already simplified. Math teacher pumpkins. I want to scare our high school students about pumpkins. After the polynomial. Then if you turn the pumpkin around, it says, because it's going to be your job in the future. That's my favorite part. Students like, oh, when am I going to have to know this? That's my high school report. Well, I've looked into the future, and your job literally is factoring polynomials. You have to sit in a cubicle for 3 hours a day and factor polynomials. Any questions? Not on factoring polynomials as a job. Like on solving this equation. Context. We set it up in a right triangle because we're talking about right triangles. We answer the degrees. That's the thing that makes most sense. That's the type of units that make the most sense for that particular context. I was also just filling time to let the gel dry so I could turn the page. Also, I was trying to frighten you with the thoughts of factoring polynomials. So the next context is we're putting the angle in standard position. We're looking at sine of theta is equal to 1/2, and theta is an angle in standard position. This is where we might want to know theta in degrees or theta in radians. Both of those contexts make sense in this problem, but I specifically requested theta between 0 and 2 pi. Oh, sorry, 360. I set my calculated degrees. I did not set my voice to degrees. That was still in radians. I was top 3 class when we were doing spherical coordinates, so I'm still thinking in radians. Hang on. Let me go into my mental setting. Mode, down, down, down. Okay. Now I'm thinking. So now in this case, we're thinking of of an angle in standard position. Which means we're going to want to think about a unit circle, which is going to give us another opportunity to practice drawing our circles. Well, I don't know about you drawing your circles. It's going to give me an opportunity to practice drawing my circles, which are a little bit dented. Fred, see, this one's got dented a little bit. I dropped this one in my mind before I drew it. It landed right on that first quadrant. So in this context, when I see sine of theta is equal to 1/2, we know that the sine is where the y coordinate. So in a unit circle, on a unit circle, sine of theta is the y coordinate. So we're looking for the places where the y coordinate is equal to 1/2. So there are two places on the unit circle where y is equal to 1/2. A place in the first quadrant and a place in the second quadrant. It makes sense that it happened in the first and second quadrants, because first and second quadrants are where y is positive, and the first and second quadrants are therefore where sine is positive. We're going to imagine, either we're going to remember we have a few things that can happen here. Either we just remember that sine of 30 degrees is equal to 1/2, and then put 30 degrees as a reference angle in the first and second quadrants. So we're going to say theta is equal to 30 degrees. Our reference angle is 30 degrees, and we're going to put that in quadrant 1 and quadrant 2. Either we remember the 30 degrees, where sine of 30 is equal to half, or we think of the triangle. Spelled or wrong. Either we just remember that sine of 30 is equal to a half, or we can use an inverse trig function like we did in the previous context, or we can just remember the triangle from the previous context to remember that these are associated. So this little green triangle is the same triangle that we had from before. The difference here is that we've got to put a 30-degree reference angle in quadrant 1 and quadrant 2. So in quadrant 1, theta is equal to 30 degrees. And in quadrant 2, theta is equal to 180 minus 30. which is 150. Either we subtract to get to the 150, or we just remember that 150 is a 30-degree reference angle in the second quadrant. Now, in this case, I specifically requested that theta be between 0 and 360 degrees. That tells you to set yourself to degrees. But the unit circle is also a place where we might have the context of radians. But the unit circle is also a place where we want to know radians. But I would have phrased the question differently. The unit circle is also a place for radians. But I probably would have phrased the problem differently if I wanted you to answer a gradient. Usually I use theta for degrees, and I use x for radians. That's not a universal thing. Theta can be radians all at once. But to draw a distinction between the two, I might say sine of x is equal to 1/2. X is angle in standard position. And x will be between 0 and 2 pi. Usually, if I want radians, I will write x instead of theta. But we changed the context of the problem. Instead of thinking about theta being an angle, acute angle in a right triangle, and theta is an angle in standard position on the unit circle. Questions? Comments? Slide remote? Deep thoughts? How's everybody still okay? I took my glasses off, so I can't see if you make the face. It's kind of blurry. See both near and far at the same time. All right, quickly flip the screen. Having eyes is such a great idea, like for biological life forms, but is so poorly implemented in humans. It's like just a mess. It's all squishy, so it gets deformed, and so all the images are blurry. And then we create forms of communication that require clear vision. Or we try to communicate at a distance where we can't see each other's faces. You know what I mean? But anyway. Soon we'll have a cyberpunk feature. We'll just install little cameras hooked up to our optic nerve. And it'll be like a $6 million. And then YouTube will be able to just like play right in our eyeballs. So they can send advertisements directly to our brain. It'll be horrible. So here's the other reason that I wanted to do this particular context, is it gives us another chance to draw a sinusoidal function. So gives us a chance to draw another sinusoidal function. Remember when we're crossing across, when we're going across the middle, we draw it with a slope of 1, and then we increase. So from the middle, we go up 1, over 1, up 1, right 1, but then we go up 1, right 2, then right 2, down 1, right 1 down 1, right 1 down 1, right 2 down 1, and so on. And then we just connect them with a curved line rather than just straight lines. So we like to draw something roughly pretty much linear across the middle when we're crossing the middle with a slope of 1 and -1. Not really slope of 1 and -1. I'm just using that from the dots. And then takes twice as long to get that second half. So here we have the graph y equals sine of theta. And we want to find the intersection with the graph of y equals sine of theta when the y-coordinate is equal to 1/2. So I'm going to draw the line y equals 1/2. And we want to see where that happens. So we can see in this first cycle between 0 and 360, we're in degrees, so I'll call this 360. We can see we get the same two solutions from before. We get 30 degrees and 150 degrees. There's this first one. Here's our quadrant 1 solution. And here's our quadrant 2 solution. There's 30-degree reference angle in quadrant 1 and quadrant 2. Same thinking that we used in the previous problem. Reference angle in quadrants where sine is positive. Here, our quadrants are laid out horizontally, though. Here's quadrant 1 from 0 to 90, quadrant 2 from 90 to 180, quadrant 3 from 180 to 270, and quadrant 4 from 270 to 360. Also note that we have 4 solutions. Because once we've gone around quadrant 1, 2, 3, and 4, once we've gone around, we get another copy of quadrants 1, 2, and 3, and 4. So quadrant 1, 2, 3, 4 here. Here's our next quadrant 1. Here's our next quadrant 2. And before this, we had another quadrant 1, 2, 3, and 4. Each time our 1/2 intersects with the graph of sine x, we're still at a 30-degree reference angle in quadrant 1 and quadrant 2. Here's another 30-degree reference angle in quadrant 1 and quadrant 2. So we get another solution every time we go around the circle. Every time we add 360 degrees, we get another solution. So we don't just get 30 degrees. We also get 390 degrees. We don't just have 30 degrees, we can subtract 360 from this. We have negative 330 degrees. And after 390, although we can't see it on this graph, if we take 390 and add another 360, we get 750. And before 330, If we subtract off a full circle, we get negative 690. And this will go on forever in both directions. That's the big change in the context here. This is only one of our sets of solutions. I got 30, the 390, the 750, and so on. And before that, negative 330, negative 650, or 690, and so on before that. So here is the angle at 390. 750 is off our chart, but before that, here's our angle, negative 330. Those are all our quadrant 1 angles. There's another one in quadrant 2, so here are all quadrant 1 angles. But we also have angles in quadrant 2, every single quadrant 2. In the primary one that we find is a 150. But after 150, if we start off with 150 and add a full circle, we're at 510. If we add another full circle after that, we'll get 870. And this will go on forever off to the right. Going towards the left, I can subtract full circles. So take the 150 and subtract. And we'll have negative 210 degrees. That will be this angle here in this quadrant 2. Before 210, if we subtract another 360, another full circle, we'll have negative 570. And this will go on forever to the left. So the way the context has changed here is that we're listing, we have an infinite number of intersections with the 1/2 and the y equals and the graph of sine theta. In the previous example, we were looking for places where the x coordinate was, the y coordinate was 1/2, because sine corresponds to the y coordinate. And I specifically restricted you to theta between 0 and 360. But on this graph of sine theta, the graph goes on forever, so the number of solutions go on forever. Every time we get to a copy of quadrant 1, 360 degrees later, we get another solution. Any questions? We can also do this in radians, where everything comes out fractions. So instead of 30 degrees, 390 degrees, and so on, I'd start off with, instead of 30 degrees, I'd write this in radians as pi over 6. Now that 390 came from the 30 degrees plus one cycle, one period, the length of one cycle. So this 390, this is 30 plus 360. That's where I get the 390. So we'll do the same thing in radians. I'll just take pi over 6 and add 2 pi. This means we have to add fractions, but that's no big deal because we have a whole number as one of our fractions. 2 over 1 is 12 over pi. Sorry, over 6. So our next one here will just be 13 pi over 6. Going backwards, we subtracted. We did 30 minus 360. So in radians, we just take pi over 6 and subtract 2 pi. We're just taking pi over 6 and subtracting 12 pi over 6. And then it comes down to 1 minus 12 is negative 11. Once we read in the fractions and we see we're just going to be adding 12 or subtracting 12 from the numerator. So after 13 pi over 6 plus 12 is 25 pi over 6. And so on. And then before 11 pi over 6, we just subtract another 12. So negative 11 and 12 is 23. Then we can do the same thing with our 150. Our 150-degree angle was 5 pi over 6. And we're just going to be adding multiples of 2 pi. And that's going to be another 12 pi over 6. So 5 and 12 is 17 pi over 6. 17 and 12 is 29 pi over 6. Subtracting, so we'd have negative 7 pi over 6. 7 and 12 is negative 19 pi over 6. And so on. We're just adding and subtracting 2 pi. Any questions? Comments? Deep thoughts? Slide remarks? Astounding observations? Incredible feats of strength? Be a funny math final exam. You can either solve this equation or bench 225. On the bench, they can't move this. Ha! It was in kilograms. That'd be a dick move. Of course, if you do that, I'm like, all right, fucking A. You get an A. What am I gonna do? Flunk someone that can bench 225 kilograms after tricking them? No. I'm just kidding. I can't be threatened. Or you can pay me this sum of money. No one can do that one. None of you have enough money. In fact, all of you don't have enough money. If you have rich parents, all of your parents don't have enough money. Because it's not just like, because it has to be like the risk is that I don't have this job anymore and I kind of need it to like pay the mortgage. So you'd have to give me enough money to essentially put me into retirement. And I'm pretty sure you don't have that. You know what I mean? I can tell because most of you are like doing homework and studying and shit. And people with billions of dollars don't have to do that. Like if your parents are billionaires, you don't have to study in school. You just go to Harvard. You know what I mean? Everybody okay? Everybody looks so very sad. You all look like this. You are like so bummed. But I know, I get it. It's afternoon, it's a math class. Some of you skipped lunch because young people don't take care of themselves. I get it. All right. That's solving equations in different contexts. I want, and it all comes down to really just one thing. Sine of 30 is equal to half. Remembering that, that's your times table, right? That's the, look at all the mileage we get out of it, just by knowing that in different contexts. It's hard to put an S at the end of words, you had all these sixes, which is the word fraction. It could have been with third. Why couldn't it have been cosine of x equals 1/2? Then it would have all been thirds. And I can say thirds, and I can't say sixths. All right. That's going to do it for today. I will see you all on Wednesday. Everybody have a good couple of days, and thanks for playing.